Thank you very much. I'm sitting in Denmark, up in the north of Europe, and it's dark outside. It's because it's 10 at night, and I'd just like to thank the invitation to present some ideas to you today. I was asked to say what my conflict of interests were. Well, I'm a retired scientist, so my only real conflict of interest is if I get my pension at the end of the month. This is the only thing I think causes conflict. Thank you for the introduction. I did worked with the IPCC for a long time, and I've also spent quite a lot of time working in France as well, where I spend quite a lot of my time these days. The important thing. Oops, we don't want to do that. Yeah, one of the things Rattenlau did not mention this, but he certainly drew attention to it. That if we look at the 17 Sustainable Development Goals that we have globally, it is very interesting, and I put little red stars on the ones which had connections to agriculture and connections to food systems and connections to the land. And you can see there must be about 6 or 7 of these Sustainable Development Goals, which are directly related to how human beings work on the land. And one of the things I think is one of the things where we get somewhere confused, I think, is this, and Professor Lau referred to this, and I would like to discuss this with him really, but we can improve the efficiency of the use of fossil fuels and sources and produce more efficiently, but does this not mean that we're going to reduce greenhouse gas emissions? So there is this trade-off really, or this interrelation between what we can do relatively and what we can do in terms of absolutes. And why is this? Well, one of the reasons why this is true is because of something called the Jevons paradox, which William Jevons was an economist in the 19th century, and he showed basically that if you improve the efficiency of things, what this did was not to decrease consumption, it actually increased consumption, because people find it cheaper to buy things, so they're just going to buy more and more. And this leads to the conclusion that I'm going to talk about, is that emissions are basically a combination both of production but also consumption. And we basically really have to think about both of these aspects, the production and also the consumption. And hopefully I can say a few words about this. I just wanted to say that with Frank, I mean, I completely 110% agree with him saying that being carbon neutral is not being the same as climate neutral. There is a lag between what happens to the global carbon budget and what happens to the global climate budget, or what happens to the global climate. And I'm very glad that he made that point. It's a very important point. There are 4 hypotheses that I have presented in different fora, and one of the things I think is very interesting is John Maynard Keynes. He was a very influential economist, of course, in the 20th century, and I'm actually writing a paper about him at the moment. But I really liked his statement. It says, "When the facts change, I change my mind. What do you do?" I think that's a very good question to ask. And I think we have seen that getting more from less, i.e. increasing efficiency, does not always lead to increased robustness, and that system redundancy is a good thing. I think we've seen that very clearly in the pandemic that we're in the middle of at the moment, or hopefully coming out of at the moment. That those societies which had put a great emphasis on efficiency, actually, when it came to this pandemic, were not very well equipped to deal with So I would say that system redundancy, having some kind of slack in the system redundancy is a good thing. There's also a discussion in ecology. I can remember when I was an ecology student that what is the position of complexity? Does complexity lead to stability? And I think that the consensus now is that increased complexity can and cannot lead to increased robustness and resilience. It can do, but it also can have a system where things get over-connected. That does not lead to increased robustness and resilience. I'm convinced now that we understand that decreased robustness, and I mean robustness is different from resilience. Robustness is like a preventative thing. How do you prevent things from happening? Resilience is how can we recover from a shock? And I think we have to think about robustness much more than we think about resilience. Decreased robustness leads to decreased efficiency. I'm convinced about that. And increased robustness leads to increased efficiency and resilience. And I think it has been clear with COVID-19 that those societies which had some inbuilt robustness actually have come out of this better than other societies which didn't have that. And what I want to do now is to talk about greenhouse gas emissions in a slightly different way than we heard from Frank. And what I'm trying to do here is trying to connect a couple of things. This is a diagram which shows the relative and total greenhouse gas emissions and how it's spread between the efficiency of production and the consumption. So, and this was developed by a Japanese scientist called Kaya. It's called the Kaya identity. And what it's doing is actually breaking down greenhouse gas emissions into these different elements. So if you reduce the greenhouse gas emissions per unit energy, and that basically has been happening, for example, if you change from coal to methane as a source of energy, if you decrease the energy needed per unit of gross domestic product, and again, in the industrialized societies since the Second World War, that's generally been the case. But what has actually happened, of course, is that GDP, gross domestic product per unit population, has increased enormously, like about twice as much as the energy per GDP has decreased. And then you've got population. So you can see if you multiply all those little elements out, then you basically come up with the greenhouse gas emissions. And it's a way of what I call deconstructing the emissions into these different factors. But this only applies, what we're seeing here only applies to the fossil fuel industry. This only applies to emissions from fossil fuels. Excuse me, I'll just have a drink of water. It doesn't actually apply to the land use emissions. And because it does not apply to the land use emissions, I was one day on my bike cycling back from the university, and I've been teaching the Kaya identity to students during the day. And then I thought, well, you could write an equivalent identity analysis for the agricultural emissions. And so I came up with this, which is basically that the yield per unit area times the energy needed to produce a particular amount of yield times the greenhouse gases that you use, or the amount of greenhouse gases you use to produce product per unit energy times the area. You can also deconstruct the emissions from land use, from the land use emissions into this identity as well. And you can see area in this case takes the place of population. This is the integration, if you like, in this what's called the Kaya Porter identity. And we had a couple of students. I did this work with Eskil Bennison in Copenhagen, and Pete Smith. I'm sure you've heard of Pete Smith at Aberdeen. He and I were the PhD supervisors of Eskil Bennison. And we were able to create these identities for different components in the production of greenhouse gases from crops. We also did it for livestock as well. And I don't actually have time to show you this, but you can see the elements that we included in this integrated Kaya Porter identity for the greenhouse gas from crops. And it allowed us to produce these kind of figures. We published a couple of papers in Global Change Biology And what was interesting, I find here, is that if we look at the relative values, if we take 1970 as a starting point, and that has a relative value of 1, then you can see that, for instance, greenhouse gas energy per produced unit has actually increased quite substantially. Total emissions of greenhouse gases from crops have also increased, but there have been some elements in this identity which have actually fallen since 1970. So greenhouse gases per land use change per produced unit. And I think it's also very important to think about the fact that many times we talk about greenhouse gases per unit area, but we really need to think about greenhouse gases per unit product. And I think Jeremy, at the beginning of the talk, when he was talking about his work in New Zealand with Fonterra, that was very interesting, I think, because of the emphasis there was on the emissions per unit product. And we have emissions per unit area, but we also have emissions per unit product. And this idea of trying to break these things down into different components can also be used in terms of the resource use efficiency. So what is the efficiency with which resources, particularly radiation, water, and nitrogen, fertilizer, are used? And you can write these kind of equations, which is trying to break down the yield per unit evapotranspiration into these other elements here. And you can draw some pretty pictures, which you can see at the bottom, where you can look at the relations between these different resource efficiencies and the trade-offs in a kind of quadrant system. And I take no credit at all for the originality of this, because this is going back to Kees de Wit's PhD in the 1950s in Wageningen. He was the first person to have these ideas about how you could deconstruct these efficiencies, these resource use efficiencies. And there have been some experimental work. This is done by Edmar Teixeira at Lincoln University in New Zealand, and Hamish Brown and other people down at Lincoln University. And one of the things I think is important here is, and what Edmar and Hamish and others were looking at was how resource use efficiencies interact with each other. Because I'm sure we would agree that resource use efficiencies by themselves, they're interesting, but what's more interesting is how do resource use efficiencies interact with each other. So here we have the relationship in the top graph here, in the A graph here, which is the water use efficiency against the nitrogen use efficiency. And you can see that in a dryland situation, this water use efficiency per unit dry matter or nitrogen use efficiency decreases. And it does here with in the dryland and also the irrigated. But when you look at the relationship between radiation use efficiency, this is then the B and C graph here, against nitrogen use efficiency, you see that the order of these efficiencies has been reversed. So here we have dry land above irrigated, and here we have irrigated above dry land. So I really think it's important that we need to think about these resource use efficiencies in a more integrated kind of way and how they interact with each other. And finally, I mean, I have not really done very much work on this, but I was thinking, how can we tie together these identities so that we have the Kaya identity here, we have the Kaya border identity here, and then we can also write identities for demand. So this is demand is animal protein divided by total protein per unit calorie per capita times population, and we can write other kinds of identities as well. And what we see here is that the same element may appear in more than one identity. And this gives us a possibility to look at the interactions between wealth, health, consumption, and greenhouse gas emissions. So what I'm trying to suggest here is that we can create a framework where we can look at these interactions, which I think are very, very important, as many of the speakers have said. Now, I'd like to just move on to talking about food systems for a couple of slides. And about 10, 15, 20, 12 years ago, we did a study actually in the European Union of the food system of Europe. And the food system of Europe looks like this. This is before the expansion of the EU. But I mean, you have a number of producers at the bottom, and then you have suppliers and semi-manufacturers and manufacturers. And then you come down to this place in the middle here, which is the buying desks of supermarkets. And then it expands from there out to the customers and the number of people who are the customers in Europe. And this is the shape of the supply chain funnel in Europe. And you can see that, of course, the power in this hourglass, it's like an hourglass, is in the center of this organization here. Maybe there may be less than maybe 1,200. It probably increased since this figure was done, but maybe there are less than 2,000 people in Europe who are basically deciding what most Europeans actually eat. And I don't want to go this in much detail, but one of the things that we were interested in when down in Montpellier, when we were working in Montpellier, was this distinction between linear food systems and circular food systems. And I think there's a lot of interest in how these two different types of food systems. This is actually from H.T. Odum's work, and there's a lot of interest in how linear and circular food systems are working. One of the things that we worked with on in the work that we did in Montpellier was what are the basic elements in circular food systems. And I think these came out as some of the 4 principles that plant biomass is the basic building block of food that should be used by humans. I mean, we talk about getting more from less, but I think the alternative is enough from less, reducing waste and increasing what we save. I mean, I think the idea that it's just more from less is a really idea which is a bit passé. The byproducts from food production, processing, consumption should be recycled back into the food system. I think we agree about that. And use animals for what they're good at. I mean, they are valuable sources of protein for many people, particularly young people and pregnant women, for example. But we need to think about how we use animals for what they're good at. And this is really some work that came from Martin Benitison, who's a professor at Wageningen in Holland. I just want to say, because I know that Geoff was telling me that there's an interest in the food systems of cities, particularly Singapore. And I just wanted to refer to a study that we did in global food security about 10 years ago now, when we looked at the food systems of three capital cities. This is Australia, which is Canberra, and the Australian capital region, and Denmark. This is if I can actually point to the place where I'm sitting just at the moment, it's just about there. And then Tokyo. We had 3 cities, Canberra, Copenhagen, and Tokyo. And what was interesting about this was how they scaled in terms of the population density. So Canberra is about 0.1 person per hectare. Denmark is about 4.4 people per hectare, and Tokyo is about 12 persons per hectare. And I haven't got time to go into the information really, but we were able to look at the food systems of these different countries, of these different capital cities, and this, excuse me, was the situation in Tokyo. Huge imports. You can see the imports of wheat in 2005. And one of the things that we also were able to do was look at how these food systems in cities have changed over time. We were able to get hold of data. And so you can see really if the production of wheat gets short globally, then countries like Japan and Tokyo are going to be having some problems because they cannot go anywhere near supplying their own needs. The only place we really found that could go supplying its own needs was Canberra. And now, after saying all that, I really want to do what I call some really out-of-the-box stuff. And this is come about by the fact that when you're a retired professor and you don't have to teach students and you don't have to apply for research grants, you have a real chance to think about some other stuff. And this has been one of the things that I've really been enjoying doing in the last 2 or 3 months. Of course, with thinking about the COVID story, the COVID-19 story. And I want to just say here that this has a connection. What I'm going to talk about here has a connection to what I was talking about with the identities. I'm basically thinking about how to use identities in connection with the COVID-19 pandemic. We talk about the race between vaccination and the social distancing measures. There's a race between the two. How many people are going to get vaccinated? To what degree do the social measures, social distancing and lockdowns and these kind of things, how do these contribute to controlling the pandemic? And I invented a V number, which I call the V number, to quantify these two effects. And it's a simple thing. The V ratio, the V number, is the ratio between the percent of the population vaccinated divided by the percent of the population as active cases. And you can get all these data off World of Data and these other websites, enormously interesting websites. And of course, the V number will increase as you increase the percentage of the population vaccinated. And the V number will increase if you decrease the proportion of the population which is regarded as active cases. And the V number will really increase if you increase the vaccinated population and you decrease the active cases via social measures. And so then I thought, well, what's the link that you could get to the V number to this R infectivity statistic? This is actually, it's in some way based on the Euler-Lotka equation for population growth, but it isn't really. And of course, you know that the R number is, if it's a value of 1, then this means that people are not transmitting the virus to another person. So as long as this value is 1 or lower than 1, then there is no spread of the virus, and the virus will eventually die out. And this is a figure that I drew, that came up with in February this year. This is looking at the data from World of Data and all these things, where I plotted the V number on the y-axis here against the R value. And this is the line, this is the regression line. And you can see that there is a line here, I've drawn this red line here, which is where we have the R value of 1 or slightly lower than 1. And where does it cross this trend line? Well, it crosses it when the V number is about 10. So the ratio between percentage vaccinated over percentage active cases is about 10 to 1. And if you do that, then you're looking at a situation in which the R number is going to be lower than 1. And then I took it all the way from January the 11th to March the 27th. I took 9 dates, looked at all the data from 9 dates. And here we have the R value on this axis and the V value on here. You can see that the V values have increased, and this is the best fit. This is the polynomial fit. And so here we're looking at a V number of about 20 to 30, which is going to give you an R number which is somewhere below 1. There's a lot of spread here. And this means that actually what this shows you is that different countries have used different measures. They've used different ways of trying to control the pandemic. And I've just had this published in it's actually a preprint journal at the moment, but it's going to be put into a regular medical journal that's when I get a bit of time. So here we're looking at a V number maybe of between 30 and 40. You would be pretty guaranteed to have an R number below 1. So my conclusions in this kind of out-of-the-box thinking stuff is that food security is certainly more than production. We have to think about food security in terms of its aspects of consumption and what does it mean for waste. How do we make robust food security systems? We need I suggest we need synthetic and quantitative methods to connect wealth, consumption, diet, and population, and maybe these identities that I've tried to show to you this morning, or this afternoon, or this evening, in fact, is something that we need to think about. I think that the mantra should be enough from less, save more, and waste less. That is the mantra that we try to live by. My wife is actually just sitting by the side of me here. So, what links are there between food systems and pandemics? I think that's a very important question for the future. I think there are some possible very interesting analyses that we could look at, the links between food systems and pandemics. Robustness is not the same as resilience. Slack and redundancy are good things. I mean, economists would say we have to run things as efficiently as possible. Well, I think they found out that that's not always the case. So even the economist, the bastion of liberal economics, says capitalism must up its game. Orthodox market economies have been useless in the current virus pandemic. A robust, flexible, resilient, and efficient food system in society needs insurance and assurance. We cannot solve current global problems with endless efficiency gains, carbon taxes, and carbon capture and storage. I mean, there's only so much carbon you can stick into the ground, and it does take an enormously long time to do that. I think Pete Smith reckoned it was about 3 gigatons per year. And it's very interesting, I think, the situation we're in now, that people are decidedly getting uncomfortable. So the question is, how comfortable do we actually feel at present in the current global situation? And I have the impression that when we started in IPCC back in the beginning of the 1990s, we were regarded as complete crackpots. And then we had this period where everybody was trying to just pull us apart. But I think that the situation is changing, and we need to change. We need to change very, 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 very fast. So with that, I'd like to say thank you, and thank you for the chance to listen to all the presentations that we've had. I think it's been enormously interesting, and I've learned something in all of the presentations that we've had so far. So thank you for that.